A colony can have too much space and still starve, not from disease, not from mite pressure, not from a failing queen, from geometry, from the precise biological relationship between the number of bees present and the volume of comb they are being asked to inhabit. When that relationship is disrupted, when frames are added before the population can justify them, the colony does not expand into the space. It contracts around the brood nest and slows. Have you seen this in your own colonies? A strong-looking hive in early spring. You add a box. You add frames. You give it room to grow. And then, 3 weeks later, the population is smaller than you expected. The brood pattern is tighter. The foragers are fewer. The colony that should have been ready for the main nectar flow is 2 weeks behind. That outcome was not random. If this channel helps you understand your colonies better, consider subscribing. This kind of timing matters every season. The mistake was made weeks earlier. Not when you opened the hive, but when you gave it space it could not yet defend. What most beekeepers misunderstand is this. Space inside a beehive is not neutral. It is not simply unused potential. Every frame added to a colony is a thermal obligation. Every empty comb cell is a surface the colony must patrol, regulate, and protect. And that thermal work cost bees. It cost foragers redirected to warming duties. It cost nurse bees pulled from feeding larvae. It cost the colony's developmental momentum at the exact moment that momentum is most critical. This is not about crowding. Crowding produces its own problems. This is about the opposite condition, underpopulation relative to space, and the biological cascade that follows. The mechanism is thermal dilution. When a colony's bee-to-frame ratio drops below a functional threshold, the brood nest can no longer be maintained at 34 to 35 degrees Celsius, 93 to 95 degrees Fahrenheit, consistently, not dramatically, not catastrophically, but consistently. And that small, sustained temperature drop across multiple developmental cycles is enough to slow larval development, reduce adult emergence rates, and compress the colony's expansion window in ways that do not become visible until the nectar flow has already begun. More bees, less honey. That is the paradox that results when timing is ignored. And the reason that paradox exists is biological, sequential, and fully predictable. If you understand what is happening inside the brood nest in the weeks before your main flowering window opens, early apiarists working in the first decades of the 20th century understood this relationship in practical terms. Field management texts from the 1910s and 1920s, particularly those produced in regions with short, defined nectar flows, consistently warned against what was described at the time as premature dilation. The language varied. The observation did not. Beekeepers working with Langstroth equipment across the American Midwest and in Central European agricultural regions noted that colonies given excess space in early spring frequently underperformed at the primary flow compared to colonies kept in tighter formation until population thresholds were clearly met. The mechanism was not fully understood in cellular terms, but the outcome was documented repeatedly. Premature expansion slowed the colony rather than accelerating it. What those beekeepers were observing, without knowing the precise biology, was thermal dilution at work. A colony that cannot heat its space is a colony that cannot develop its brood at full rate. A colony that cannot develop its brood at full rate cannot reach foraging strength before the bloom. Growth without timing is loss. That observation, made in field notes over a century ago, maps directly onto the biological mechanisms we can now describe in precise developmental terms. To understand why early frame addition slows growth, you need to understand what the brood nest requires to function correctly. Worker brood requires a sustained internal temperature of 34 to 35 degrees Celsius, 93 to 95 degrees Fahrenheit, from the moment the egg is laid through the capping of the cell. That window spans 9 days for the open larval stage. Below 32 degrees Celsius, 89.6 Fahrenheit, development slows measurably. Below 30 degrees Celsius, 86 Fahrenheit, developmental deformities begin. Even small, repeated temperature drops within the acceptable range cause extended development time. Larvae that should emerge on day 21 emerge on day 22 or 23. And those extra days of developmental lag multiply across an entire brood frame into a meaningful population deficit. The colony maintains this temperature through a combination of metabolic heat generation and physical clustering. Bees press against one another, against the comb, against the brood, transferring body heat to maintain the thermal envelope. The more bees present per square centimeter of brood surface, the more efficiently this heat is maintained. The fewer bees per unit of brood surface, the harder each individual bee must work to compensate. When empty frames are added beyond the population's capacity to cover, the bees must allocate workers to patrol and minimally heat that expanded space, drawing those workers away from the brood cluster. The brood nest does not expand into the new space. Instead, it tightens and under sustained cold pressure may contract further. This is the central failure of premature expansion. The beekeeper sees empty frames and interprets them as opportunity. The colony sees empty frames and registers them as thermal liability. There is a threshold below which frame addition becomes counterproductive, and it can be measured directly at inspection. A colony should cover a minimum of 8 standard Langstroth frames, deep frames, fully occupied by bees on both sides, before a second brood box is added. In practice, most experienced managers working with short flow regions set the threshold at 9 to 10 frames of bees, not frames of drawn comb. Frames of bees, meaning frames where the bee density on both faces is sufficient to constitute what field terminology describes as a frame covered in bees. If a colony is running at 6 or 7 frames of population in early spring, and frames are added to encourage expansion, the population per frame drops immediately. The colony's thermal capacity is diluted before the population has generated the numbers needed to absorb that dilution without developmental cost. The correct threshold also depends on ambient temperature. In regions where nights are regularly dropping below 10 degrees Celsius, 50 Fahrenheit, even in spring, the thermal demand on the colony is higher, and the expansion threshold must be adjusted upward. A colony that could safely manage a 10-frame box during stable late spring conditions should not be expanded to that configuration when nights are still cold and daytime temperatures are variable. The mistake happened weeks earlier. This is critical to understand from a seasonal management perspective. A colony's condition at the nectar flow is not the result of what you did at the nectar flow. It is the result of what you did 4 to 6 weeks prior, during the brood cycles that built the forager population that will be present when the bloom opens. Consider the timeline. In a temperate climate, with a primary nectar flow beginning in late May or early June, driven by white clover, black locust, or linden, depending on region, the forager population working that flow was brewed in late April. Those bees were eggs in the 3rd week of April. They were larvae through the final days of April. They capped and developed through the first days of May. They emerged in mid-May. They spent their first 3 weeks as nurse bees and hive workers. They transitioned to foraging in early to mid-June, precisely when the main bloom is producing maximum nectar. That biological sequence has no shortcuts. A bee that will forage the linden bloom in early June must have been a healthy larva in late April. If that larval development was slowed by thermal dilution because frames were added too early, in late March or early April, before the population could support them, those bees emerge later, transition to foraging later, and are productive for fewer days of the bloom than they should be. A bloom window of 10 to 14 days, common for single-source flows like black locust, tolerates almost no developmental delay. Every day of forager misalignment represents lost collection capacity that cannot be recovered within that season. This is the income risk for small-scale producers that rarely appears in calendar-based management guides. The flowering window does not wait. The bloom does not extend itself to accommodate a colony that is 2 weeks behind schedule. The nectar is produced, peaks and declines on botanical timelines that are only loosely correlated with what the beekeeper intended for colony development. A single mistimed expansion decision in late March or early April can shift a colony's peak foraging capacity outside the peak of the primary bloom. The resulting harvest reduction, compared to a correctly managed colony of equivalent genetics in the same apiary, can be 30 to 40% of the expected yield from that hive. For a small-scale producer running 15 to 30 hives with limited operational margin, that kind of colony-level underperformance, multiplied across several hives, represents a meaningful loss of seasonal income. Understanding the inspection sequence that leads to correct expansion timing is therefore not a technical nicety. It is a production decision. At first inspection, typically when ambient temperatures allow hive opening without cold stress, generally when daytime temperatures are consistently above 14 to 15 degrees Celsius, 57 to 59 Fahrenheit, the target assessment is population distribution, not brood volume. Pull 3 to 4 frames from the center of the brood nest. Examine bee density on both faces. Count brood frames. Note whether the bees are covering the outer frames, or whether there are uncovered frames at the periphery of the box. If the outer 1 or 2 frames are uncovered, even if brood is present in the center, the colony is not ready for expansion. It is managing, not growing. It is maintaining heat in a configuration that has already reached its thermal limit. Adding frames at this point extends the uncovered perimeter and increases the area the bees cannot efficiently heat. The correct intervention at this inspection is consolidation, not expansion. If the colony is running 7 covered frames in a 10-frame box with 3 uncovered at the edges, the uncovered frames should be moved outward and replaced with frames of drawn comb moved inward, contracting the effective hive space rather than enlarging it. This concentrates the population on the brood nest, improves thermal efficiency, and accelerates the brood development that will produce the population increase that justifies expansion. This is counterintuitive for beekeepers trained to think of hive management as progressive addition. But the biological logic is precise. Thermal efficiency increases developmental rate, which increases population, which produces the conditions under which expansion becomes genuinely productive rather than counterproductive. The second inspection, typically 14 to 18 days after the first, is the critical decision point for spring expansion. If the colony has responded correctly to consolidation, if the population has increased to the point where it is covering 9 to 10 deep frames and brood frames are showing solid, continuous capped brood across the face of 3 or more central frames, expansion is now justified and in fact necessary. A colony that is fully covering 9 frames in a single deep box is approaching the edge of productive congestion. The queen's laying space is becoming restricted. Nurse bee density is reaching the threshold at which swarm preparation may begin. At this inspection, the intervention window for adding a second deep box or a first honey super, depending on local management practice, is narrow in both directions. Add too early, and thermal dilution slows the developmental momentum the colony has just established. Add too late, and swarm pressure begins to compete with foraging momentum. The indicators for correctly timed expansion at this second inspection are specific. At least 9 frames covered by bees on both sides. At least 3 frames of solid capped brood, with low percentage of empty cells, less than 15% gaps. Queen activity observable or recently confirmed. Brood nest honey stores at the periphery of the nest, indicating colony is not feed limited. No visible queen cells in early development on the bottom bar or face of brood frames. If all 5 of those conditions are present, expansion is the correct action. If 2 or more are absent, wait 1 additional inspection cycle, 7 to 10 days before reassessing. The mistake progression model in premature frame addition typically follows a pattern that is consistent enough to be useful for diagnosis after the fact. In early season, late March to mid-April, in temperate regions, the beekeeper opens a colony that looks populous on its cluster. There are bees, there is brood, there is visible activity. The instinct is to give the colony room to grow. 2 additional frames of foundation, or partially drawn comb, are added to the brood box. The hive is closed. The beekeeper feels they have done something productive. Within the first week, the bees spend significant foraging hour equivalents, producing wax to draw the new foundation, diverting metabolic resources from brood care and thermoregulation. The brood nest temperature fluctuates during cold nights when the cluster thins to cover the expanded frame count. Development in the outer larva slows by 1 to 2 days. By mid-season, 3 to 4 weeks later, the second inspection reveals a brood pattern that is slightly thinner than expected. The beekeeper may add a second box at this point, compounding the problem, because the colony still looks populous and the logical assumption is that it needs more room. The colony is now running 2 boxes that it cannot consistently heat, and the forager development curve has been shifted approximately 2 weeks behind schedule. By late season, at or after the main nectar flow, the colony collects less than its genetic potential would suggest. The population is not dramatically smaller, but the foraging cohort, the bees aged 17 to 42 days, that constitute the actual production workforce during the bloom, is smaller and less synchronized with the peak of the flow than it should be. The loss is structural. It was built into the season in April. There is an additional risk layer that compounds the thermal dilution problem and is frequently overlooked: the interaction between premature expansion and varroa mite population dynamics. A colony running at reduced thermal efficiency and slower brood development has an extended proportion of open brood at any given inspection. Longer developmental timelines mean more days of uncapped larval and pupal exposure, the stage at which varroa mites reproduce. A colony that should be producing capped brood at optimal rate and transitioning larvae through the pupal stage in 12 days is under thermal dilution, producing brood that takes 13 to 14 days, and that additional window of open brood at scale accelerates mite reproduction across the brood nest. This is not a primary mechanism, and it is not always significant enough to be operationally decisive, but it matters in apiaries where varroa pressure is moderate to high, and it is one of the reasons that colonies started in poor spring management conditions sometimes present with elevated mite loads before summer. Not from treatment failure, but from the extended open brood exposure that thermal dilution produced weeks earlier. The correct response to this risk is not additional treatment, it is timing correction. Restore thermal efficiency through consolidation. Allow the colony to reach the population threshold where expansion is productive, and the brood cycle will normalize. The mite reproduction advantage disappears when the developmental timeline returns to its correct parameters. Every 3 to 4 minutes in this analysis returns to the same point, because the biology returns to the same point. Timing is not a secondary concern, it is the mechanism. A frame is not a neutral object inside a beehive. It is a unit of thermal obligation, a unit of patrol coverage, a unit of wax production demand. Adding frames before the population can absorb those obligations does not accelerate colony development. It fragments the thermal envelope, dilutes nurse bee coverage, slows larval development, compresses the developmental curve, and misaligns the forager population with the bloom. The colony does not fail visibly or suddenly. It simply underperforms, quietly, biologically, in ways that are invisible at the hive entrance, and only apparent at the extraction table weeks later. For small-scale beekeepers with direct dependence on seasonal yields, particularly those managing single-flow apiaries, or running fewer than 30 colonies where each hive represents a meaningful share of annual production, this quiet underperformance is not an abstraction. It is the difference between a viable season and a marginal one. The corrective framework is not complicated. It is primarily a matter of measurement. 1. Assess population on frames covered, not visual impression of activity at the entrance. 2. Require a minimum of 9 frames of covered bees on both faces before adding any expansion space. 3. Lower that threshold in variable spring weather. If nights are below 10 degrees Celsius, hold expansion until consistent overnight minimums are above 12 degrees Celsius. 4. Confirm queen activity and solid brood pattern across at minimum 3 central frames before making any expansion decision. 5. Inspect on a 14-day cycle during the critical pre-flow period. Do not extend inspection intervals beyond 18 days during this window. The developmental cycle is 21 days. Missing a full cycle means missing the intervention window entirely. 6. Add expansion space in increments, 1 box at a time, confirmed covered before the next edition, not 2 boxes at once, because the hive looked strong and the season felt right. 7. Remove expansion space that has not been populated within 3 weeks of addition. Empty drawn comb in an underpopulated hive is a liability, not a resource. These are field-applicable parameters derived from the biological requirements of brood development, not from opinion or tradition. The hive opened in late April that shows a solid 9-frame cluster, bees on both sides, queen laying in an unbroken pattern, honey stores on the outer frames. The low hum of a colony running at thermal capacity is a different object from the hive opened 3 weeks earlier, with 6 covered frames and 2 additional frames of foundation added by a hopeful hand. One colony will be at the bloom on time. The other will arrive late to a flowering window that has already peaked. The bees have not changed. The biology has not changed. The bloom opens on botanical timelines that precede beekeeping by millions of years. What changes? What the beekeeper actually controls is the degree of alignment between colony development and the flowering window that represents the season's production window. That alignment is not achieved by optimism. It is not achieved by adding frames because it seems like the right time. It is achieved by measuring population against thermal requirements, by understanding the developmental timeline that builds the forager population that meets the bloom, and by resisting the instinct to expand before expansion serves the biology. The mistake happened weeks earlier, knowing it precisely, knowing why it happens and when, is the only reliable way to prevent it.